Everyone, July 22nd. Alright, back at home. So the goal is we do this and we need to start working on this thing. At least, I mean, I probably won't be able to do everything in one shot, but at least we need to get the binary lifting set up, the lowest common ancestor set up for this. It will be, now I have this one still here, so I kind of give you a little bit, give myself a little bit hint of how to do this. But I think I still have the general idea of how this is supposed to work. Not exactly sure, but I think I do. But might have to go back here just to get a look again. But anyway, so we'll do that. But let's solve this one first. Sort array by increasing frequency. Given an array of integers, sort the array increasing order based on the frequency of value. If multiple values have the same frequency, sort them in decreasing order. What does that mean? So we have 3, 1, 2. Sort in decreasing order. Okay, so basically we will do, again, it's a custom, so we need to get their frequencies, right? We get their frequencies and we'll sort, and based on A, B, and there will be .get, and if they're, well, I guess in this case maybe it's easier just to write a comparator. So we have to go back to the same thing, because I don't really know how to write comparator. New comparator, so I can just do this. Okay, new comparator, compare integer. Okay, so I can just write this. Okay. Okay, so we're looking at is frequency. So I need to get a frequency. Number is this. So yeah, let's just do a map. Easier to reason, right? So this will be a counter, right? For int n of nums, counter dot put n, counter dot get all default and 0 plus 1. Okay, that's the counter. And then what we need is to sort this nums, but we cannot sort it directly. But what we can do is turn it into an int. I like to turn this, right? Nums with frequency. This will be nums.length. This will be 2, right? For int I, 0i smaller than nums.length I plus plus. Okay, so we say nums I shall equal, no, not nums I. Nums with frequency I shall equal to new int. So I'll put nums I at the front, and then counter dot get. Ooh, that's actually not right, because no, it is right. It is okay. because you're sorting, right? So frequency, small frequency goes before, and then if the frequency are the same, then we sort based on this. And I guess it should be fine. Dot get numzi. So we'll have like repeats, but it's okay. Alright, this is okay. Okay, then we say arrays dot sort nums with frequency, and here we'll say new comparator. Okay, so new comparator t, that's not integer, this is going to be int, right? And new comparator, and I'm going to say public int compare. Public int compare int a int b. Alright, then we'll compare the count, right? So if a1 is equal to b1, right? So the count is the same. Return counter the same, return b0 minus a0. I also return a1 minus b1. So we sorted it, and then int rest equal to new int nums.length for int I 0 smaller nums.length plus. We basically is going to do res I equal to nums with frequency I 0. Turn res. Okay. Let's see, it's basically a Java skill practice. Okay. $16.36. This is more of a Java skill practice on custom sort. Alright, let's see. Is that right? That's decent. Oh, you can do lambda directly. Okay. You can do lambda directly. Okay, so this is the real deal now. Do we have this 2846? No, we don't have. Two 846. Alright, the goal is very simple. We are going to just start building it out. It's going to be a complex stuff. But the first thing we're going to build out is a question which is def kth ancestor, right? Ancestor. K. Some nodes K. So we have the node and K. And this one will return integer. Alright, so let me get the question again. Are the values unique? Yeah, because the nodes are represented by numbers. Right? Nodes are represented by numbers. So I need to get the graph. Yeah, I need to get the graph. And then once the graph is done, we need a matrix, which is the value. Okay, hold on. 0 to n minus 1. 0 to n minus 1. So each one will have its matrix. It's going to be a DFS, right? It's going to be a DFS to get all its ancestors. Okay, so we need to create the graph. Okay, I need to create a graph first. So there are a few things. Like for this case ancestor, I need to know the node, I need to know the K, and on top of that, I need a graph, which is going to be a dictionary of. You're gonna do dictionary? Yeah, dictionary of list. I mean, there's no point not to do it, right? N is 10 to the 4th. Yeah, that's just a dictionary. Alright, so that's the graph. What else? I also need a matrix. N matrix. This is gonna be a dictionary of wait, is that a dictionary of list? No, this is going to be, what is this? You're given an n, right? Yeah, given an n, let's just do list of list. Alright, so we have this, but first of all we need the graph. Default dict. So we'll do default dict, a list, then for, oh holy crap, because I need to reuse it, so it's gonna be a list of tuple. It's not a list of int. A list. That's a graph. I already said it's not gonna be. Man, you didn't listen. It's gonna be a. List of list, right? But it's gonna be a list of tuples. Int and int. So I need to put the weight in it as well. And as we go through, yeah, I'm gonna go through twice. Anyway, so graph is this. So for E in edges, alright? So E is gonna be U, V, and W. Undirected. Damn. UVW. Okay. So graph. Okay, I think I can do this. UVW in this. Okay, so U dot append tuple VW. Okay, V dot append tuple UW. Right? It's because we have to be yeah, I don't need the for dict, so I don't need this. Don't need this. So then yeah, then when we iterate through, we just make sure we don't go check the parents. It's slightly more complicated. It's okay. Okay, so this is the graph. Look at the graph. Enjoy. Okay, I'll browse that. Okay, so this is the graph, and after I get a graph, I can start. Let's start writing the kth ancestor. And do the kth ancestor, I need to create other functions, right? So I need a function of, let's call it the generate gen ancestor matrix. Ancestor matrix is generated by I need a node, I need a graph. Maybe I can do or how do Python do custom type? Type something. Okay, so we're gonna say type graph t equals, so basically it's the entire stuff to this. Invalid syntax. What? No, has to be 3.12 plus. How about before? Data class. No way. There's no way to do generic. Yes. Type var. Okay, that's not what I want. Use type variable for complex type. A variable complex type. Yes. Type alias. Oh, you directly do it that way. Okay, so I don't have to use this. Okay, then I can just go graph t, right? So I can go graph type. Yeah, so I'm gonna say ancestor matrix t list int, right? And now we can make make this much easier. Ancestor matrix. Matrix, I can just call it mat. Okay, so I don't like to mat t. Okay, so all the matrix we're gonna call it mat. Okay, mat t. Good. So graph t, and do we modify the ancestor matrix? Yes, I believe so. Ancestor matrix. I believe this one doesn't return anything. Okay. So first of all, this will just go past. And here, the graph t will be graph t. And then we'll say ancestor matrix will be ancestor matrix t. Same thing for in range n. Then what? We have the node, we have the graph. We have the node, we have the graph. So what we want is parent. I need a parent. So node, parent, and a graph. So when we get to the current node, I will push, and we can go back. Right? It's just a tree. It's a tree. So there's no. So if it's a tree, it always goes down. So all I need to check is if it doesn't go backwards, right? So everyone we can have many connections, but at the end of the day, if it's a tree, to avoid a looping, I just need to check if the parent is not in my child, then that's good, right? That's good. Okay. So what we gotta do now is ancestor matrix. We need to push the current one into it, right? So we need to say ancestor matrix node dot append parent, right? So this we can call it the 0th ancestor of node is parent. Not 0th, it's 2 to the 0s, right? 2 to the 0th ancestor is parent. So once we set that, then we can go through, but I also need to know which level it is, right? We need to know which level. So I need to know its level, and I need to go until the level cannot allow. Right, so I need to know the level, which means we need to know level. Okay. Then we should say for I, right, in range 1. So we say for I in range, from 1 to, actually it's easier if I just say I equal to 1, while 1 left shift I is smaller or equal to the level, right? If it's smaller or equal to the level, then we say ancestor matrix node dot append who is the ancestor. Current ancestor shall equal to ancestor matrix. So ancestor matrix node I minus 1, right? It's I minus 1. That's right. So to find out, this is the binary lifting part. So we get the current node's ancestor, but it's I minus 1th ancestor. So it's not, because we want to find its ith ancestor. So we find its I minus 1th to the I minus 1th ancestor, and I'll find its I minus 1th ancestor, and that will be the current ith ancestor. So I do that, and I plus equal 1. Okay, so now we're done with this. We're gonna check its children. So for child, we don't need to know the weight in graph node. If child is not equal to parent, we say self dot generate ancestor matrix node be child node level plus 1 graph ancestor matrix until we're done. Okay, so that will be to generate the ancestor matrix. So for here, I'll do let me remove this. It's okay. We don't need this. Generate ancestor matrix. And then we do self dot gen ancestor matrix. A node, which is 0. It doesn't really matter from which one. Parent is 0. 0 graph ancestor matrix. Okay, and then we need to say generate the frequency, right, of each of the paths to each node. Self dot generate path frequency. I don't know what this one is gonna do. So say def gen path frequency self node parent level. Do we need level for this? Oh, I need a level as well. Gosh, dang it. Yeah. Levels. My bad. Levels node goes to level. Okay, we get the levels. Here, levels. Okay, so this, we have this, and path frequencies. Actually, this is going to be... What's path frequency? Okay, path freq t. I think it's going to be a list of counter, right? Because we just need to know the weight. 1 to 26. Okay, path frequency, done. Path frequency. Again, we're not returning anything. Okay, so we need a path frequency. So if we need a path weight frequency, path weight frequency, that's fine. It's a path frequency. It's the weight. So as we go through, we have to have the current frequency, right? We have the current frequency, and then when we hit the node, we'll push it in, right? And then we keep, and then we have to, yeah. So path frequencies, current frequency, right? So we need to know a path frequency, current frequency. Just gonna be a list of int. Right, so we collect. So when we hit the node, we already have it. Right, we already have it. So we just say path frequency node equals to current frequency. Copy it. Right. Then for child weight in graph node, if child is not equal to parent, then if child is not equal to parent, then we say current frequency weight plus equal 1, then self generate path frequency child node path freaks, and then current frequency, right? Once we're done with this, then we say current frequency weight minus equal 1. We go to the next one, right? Because it has to happen after the first one. Yeah. Oh, but counter, you can directly do arithmetic. Yep. Counter, I think, is easier for this. From collections port. So path frequencies will be a counter, right? Okay, so how to create a deep copy. I think this should be fine, right? Actually, it's a good question. Okay, this is one. This is what we're doing right now, and we say bar equal to full.copy. Okay, bar is the same. So bar 2, let's say equal to this. I think shallow copy is enough. Shallow copy is enough, more than enough. So I don't need to do this. I can just say current frequency.copy. And undefined graph. I didn't have a graph. Damn. Graph T. Okay, and that's it. Right, this is what we want. So we'll get we need a path frequency. Path freaks. Path freaks T. Okay. Oh, that's not right. My bad. Counter. And this we're gonna do 0. Parent. Graph. Path freaks. And counter. Okay. 1, 2, 3. Okay, that's it for today. We just started. There are a lot more to go through in this. We'll do